logarithmic inequality. If x and y are two positive numbers such that x is greater than y, guys. And the first rule of logarithmic inequality says that if you take log x and log y of the same base, of course, the sign of the inequality would be same. What I mean to say, if suppose if x is lesser than y, obviously both are positive here as well, and log x would be lesser than log y. If x is less than equal to, log x would be lesser than equal to log y. Sign won't change. In what case? What is A? A is, guys, A is greater than 1. Now why, that we will see. Before that, just to explain this, let's take an example. Now other thing is, if x is lesser than y, log x is lesser than log y, it works both sides. Like if log x is lesser than log y, then x would be lesser than y. For example, log x minus 1 base 3 is greater than equal to log 11 base 3. The question is, we have to find x. So using this property, we can remove log both sides, and which sign will come here? Since what is base here? Base is 3, which is greater than 1, so the sign which will come here would be greater than equal to 1. So x is greater than equal to 12. In questions where logarithm is involved and the argument has the variable function or something in terms of variable x, we also need to ensure that the argument, which is x minus 1 in this case, should be positive, and the answer should always be inside the domain of this. Finding the domain of logarithm means equating the argument greater than equal to 1. So x greater than 1. So if you take x greater than 1 intersection, you will get x greater than equal to 12 only, which is the answer. Okay, guys. So had it been like this, let's say if we reframe this question like this: log x minus 1 is less than log 11, again base 3. So since again base is 3, we can remove log both sides. Sign of the inequality would be as it is, guys. So here you will get x less than equal to 12. Now, as I said, we have to check the argument. We have to check the argument. We have to impose the argument has to be positive condition, which is what we call domain condition. So x greater than 1. So x greater than 1 is, let's say, 2. So if you take the intersection of first and second, x greater than equal to 12 and x less than greater than 1, you will get x greater than 1 and less than equal to 12 as the answer. So this is one way of defining the inequality, logarithmic inequality. What if the base is not greater than 1? What if it is lesser than 1? Let's see that case now. So x greater than y, both are 0, greater than 0. If we are taking log x, log y, from here to here, x greater than y to log x, log y. Now if I choose a to be between 0 to 1, the sign of the inequality would get reversed. What I mean to say is, if x is greater than equal to y, the sign would get reversed, but after taking logarithm it will become less than equal to. And this also holds in the reverse way, like if log x is lesser than log y, x is greater than equal to y, that also we can do. This holds for 0 to 1. As I said, how it came, that also we will see. Let's take some example to understand what exactly it is. For example, log 4 greater than 1 by 2 is greater than log x greater than 1 by 2. The question is, what is x? Find x. So what will come in the next step? Since the base here is half, which is a fraction between 0 to 1, the base is between 0 to 1, therefore the sign of inequality, as we have seen, that if it is less than, it will reverse. So here it becomes lesser than, and 4x, x greater than 4. This is also satisfying the domain of this, which is x greater than 0, because if you take x greater than 0 and take intersection with x greater than 0, you will get x greater than 4 only. So this is the first set of rules of logarithmic inequality. Now, as I said, how it came, guys, let's see. Let's say this is x-axis, guys. This is y-axis. Like this. Okay. Now, if I draw the graph, if you remember the graph of log x, it is like this. Okay, this is graph of log for a greater than 1, guys. Now if you take 2 points x and y on this is x, y can be taken this side also or this side also, it doesn't matter. So this is, I will join this with this and join this with this and this with this, guys. Now this is x, this is y, guys. So this length is log x, guys, and this length is log y. This is the graph of what? This is y is equal to log x base a function where a is greater than 1. So as you can see clearly that if x is greater than y, log x is greater than log y. Similarly, if log x is greater than log y, if log x is greater than log y, x greater than y, we will get. So that's how it came, guys. Okay, now if you take graph for a 0 to 1, y is equal to log x base a, that the second property can be established, in which the sign gets reversed. Okay, and this one in which sign doesn't change, the proof is this. Okay guys, let's take an example now. Log 7 greater than log 2 base 4x minus 3, 4x minus 3, find x. So how we can do this, guys? So yes guys, if the question is, if this equation logarithmic inequality is consistent, or if it has a solution, the next step should be this. It should not be this, because otherwise it won't have any solution. So since the next step should be this, the next step should be this from here to here. Therefore guys, 4x minus 3, obviously the base should be what? Greater than 1 or lesser than 1? Yes, it should be greater than 1, guys. So adding 3 both sides, we will get this, and multiplying by 1 by 4, you will get this. So from here to here, and from here to here, what we did, guys? We added 3, we multiplied by 1 by 4. So x greater than 1 is the answer. Okay guys, now if the question is like this, log 7 base x is greater than equal to log this view won't work here, guys. You will see this. You will see this in some other property, guys. As of now, that's it. You will see the next inequality, which is derived from the same what we did. Little bit, it is a different version of the same property that we did in inequality, logarithmic inequality 2. We will see that.